When it comes to 3D printing, I'm not a complete beginner. In fact, my first dive into the world of sim racing, 3D printing was actually integral to the setup of my rig. A lot of the components that I handle when I get into the sim were actually 3D printed at home. Things like my kill switch, the shrouds for the fan simulator, as well as the enclosure for the button box. After a while, you start to see a bit of a pattern. You eventually just start making little gizmos and gadgets and boxes for things. And while printing things for my simulator has been very enjoyable and rewarding, I've always wanted to push things a little bit further and print parts that I can actually use on my race cars. Functional aero, cooling ducts, interior trim, these are just a few of the things that are now becoming feasible for prosumers or enthusiasts to start printing at home. There is a little bit of a problem though. I have very limited CAD experience, but I'm willing to fail and then fail and then fail and fail again, and then maybe win? So what's the goal? Well, I want to design and print as many parts as I can to support my own K24 DCT turbo swap into my FRS. And to kick off this journey, I got myself this. The X1C from Bambu Labs. Just to be clear, I pay for this unit with my own money to show you guys the reality of what it takes to set up one of these and start printing your own parts. The first project that I'm going to tackle in building my K24 is actually balancing the new connecting rods. Now, you could just slap in the rods as they come from the manufacturer, but the tolerance could be plus or minus 1.5 grams between the rods. A lot of aftermarket engine builders will target within 1/10 of a gram. And to make this happen, you actually do need a bit of a jig to get accurate measurements. And while it's a simple device, if you look online, these things can cost way more than you would ever imagine. And it's just these little tools and little parts that start to add up at the end of the build, taking up a significant part of your budget. So I'm going to be building my own. But that's not going to be all that we're making. If you've been following the channel for the past little while, you'll know that I actually do quite a bit of amateur racing. And one of the teams that I race with is M-Tech Racing in their Audi TT Endurance race car. So at the end of the episode, we're actually going to be hand delivering some parts over there to install on that car for the 2025 season. All right, let's get this thing unboxed and built. This Bambu Labs unit came with many unlisted extras to help you get started with printing right away. 3D printing has come a long way in the past decade, with many units now marketing the promise of just plug it in and print. Regardless of the brand that you choose, filament management systems are becoming more common as this enables unmonitored swapping of filament types and colors in a single print job. But these extra features comes with more reliance or forced interaction with connected services. While auto calibration is convenient, it does take a long time to complete. Expect a printer to take 15 to 20 minutes to calibrate on first startup to sweep through a series of movements and leveling tasks. To put the printer through its paces, we'll go with the classic benchy boat print, which takes about 25 minutes end to end. Alright, so here's the first print, and honestly the quality is pretty amazing for the stock nozzle of I believe is 0.6 millimeters. It isn't perfect. As you'll see, there is one horizontal band that I see, x-axis band, but otherwise the detail for, just the test print and for things that we want printed very, very quickly with PLA, I mean, it's pretty amazing. Now, after doing a bit more research, it turns out the line is a known issue with the print file known as the benchy hole line. In short, this is the plane where the print transitions from partial infill to solid. Because one of the things that we're going to be doing in building automotive parts is using engineering filament, and what I mean by engineering filaments is that these are filaments that have, for example, glass fibers or carbon fibers mixed in to give it different properties that are useful for us for automotive parts. And what we have to do in terms of treating that filament is we want to manage the moisture. They tend to be a little bit more sensitive to having moisture in the filament from being absorbed in the environment that you're in. And why does moisture matter? Well, the head is extruding over 200 Celsius, and if there's moisture in the filament, you can kind of fill in the blank. So the additional piece of hardware that we have to manage that is this filament dryer here, and all it does is basically it heats up inside the chamber. You can put 4 spools in there, and we can actually route the filament spools directly from this dryer into the printer itself, and that will play well with the AMS because that auto retracts every single time. All we had to do was print out this separate piece right here, a Y splitter for the filament that will take 2 feeds and put it into one. While side loading from the dryer is convenient, you do have to manually retract the filament if you want to switch to using the automated filament system, a fairly small price to pay. Now that I'm pretty satisfied with the printing experience and the output that the printer is generating, we're going to start moving into CAD and designing the actual file for the balancing jig for the connecting rods. And the software we're going to use today is Autodesk Fusion 360. The nice thing about Fusion 360 is that it does have a free version for hobbyists, and because it's a fairly popular piece of software, you'll be able to find a lot of tutorials online to help you get started. Now, the most popular style of this jig is fairly straightforward. A platform with a large rod, a U-clamp to use as a slider, a swivel on bearings, and a large end insert as well as a small end insert, and another platform to rest on top of a scale. The only parts that we won't be able to print are a couple of bearings that can be found for a few bucks on Amazon. To kick things off, let's try something simple, like the circular inserts. Alright, so these 4 items are the first things we're going to try and test. So small end insert, big end insert, and some fasteners that we're going to print as well to reduce the amount of stuff that we actually have to purchase. Once we finished our design in CAD, we then turn to our slicer, which turns the design into instructions for the printer. This is where we'll get a time estimate as well as a filament weight and cost. Another useful invention in recent years is the magnetic build plate, which allows you to more easily remove your parts after the print. So the inserts worked out quite well, with the bearings fitting like a glove. However, not everything was this simple. Our first attempt at making threads was a complete failure. The tolerances were too tight, likely an issue with the thermal expansion that occurs with prints. So we tried again. Only this time we offset the top and bottom faces of the threads by about 0.1 millimeter. This small change gave us a smooth interface between the nut and the bolt. Yo, check this out. Almost went down the drain.
Oh, damn, look at that.
It's pretty smooth now, right?
That's pretty dope. Is this the smallest you can do?
I could probably go smaller, but it gets harder and harder.
With the threads, eh?
Yeah.
Did you make this on CAD?
Yeah.
Let's put on a stress test. Let's put on a car.
Alright, I'll see if I can catch this thing. Why don't you drop the camera as I try to catch it? Ah!
Let's get on.
With the hardware and the inserts out of the way, we then designed the rod and support bases. Then we finally figure out threads, and we got it on the first try. So let's move on to the next piece, which is going to be a sliding clamp to hold the swivel mechanism. Okay, so here are some of the complexities of 3D printing. We have this upright piece here. It's going to slot into this base. We're going to flip that, 90 degrees. The issue with 3D printing is that, especially when you're doing threads, it likes to print with your Z-axis kind of layering up this way with the threads pointed upward. Now, the issue with this piece is that for me to secure it to here, I'd like to put another thread underneath for another thumb screw. Now, this thread is going to print in this orientation. Now, when you do that, you're going to have overhang at the top of the threads. So this is actually going to be a pretty good test of whether this printer can handle this kind of overhang for a thread. It's possible that we'll have to chase it with a regular bolt afterward, but hopefully we don't have to get there with the tolerances that we're going to build in, offsetting the faces of the thumb screw itself. So we'll give it a shot and see how it goes. Initial results on the big end piece here. It's actually not bad. I think one thing I'll have to do is create a little bit more offset. Basically about right there, I think that gap is probably not sufficient for some larger pistons, but I don't know, we'll mock it up and see what it looks like. So this is what it looks like right now. Probably add maybe another 2 or 3 mils of offset there and then we should be okay. So, I think we just got our first print failure. Let's take a look. Oh boy. Look at this mess of spaghetti. How did we get here? Well, I got an alert last night that the power went out on the print on the mobile app, and it did suggest that if the print didn't move, you can actually resume from where it had left off. And from the monitoring of the print, it looked okay. But I think what happened was the bed plate had cooled off, basically back down to ambient temperatures, and the parts were essentially just floating on the build plate. And so when the nozzle, the hot end, came down to touch the part again, it knocked everything loose and then ended up with what we see right here. Let's do a quick comparison here. On the surface, these look identical, but you can see here, last time I built this piece, we had a little bit of an issue with the overhang in the countersunk part of the part. What I did this time was printed some support. Now, my big worry, you can probably imagine, is whether this support is going to release easily. So let's give it a shot. Well, maybe that was just some beginner's luck. Quick comparison, much cleaner on the new part. So here is our U-clamp piece for the rod adjustment, and first impression is that it's probably too much slack. I did 1mm clearance, hoping that the thumb screw would be able to take up the slack, but I think what we'll try now is 0.1mm clearance, and then hopefully that is enough for the clamp to do its job of staying put. A bit of an issue for me when modeling is that I very easily get motion sickness, or more accurately simulation sickness. And a lot of that comes from just using, a regular mouse like this. When you are using the orbit function, the sensitivity, sometimes you start whipping and zipping a lot faster than you intended to. So I end up getting this, the 3D Connection Spacemouse, which is pretty industry standard for modeling. And what it'll allow you to do is have this, knob thing on your left hand and then a mouse on the right, and you can use that in conjunction to do your modeling, and it'll be a little bit more accurate in terms of actually making the movements that you intend to make. I have to admit, it will take a while to get used to this new tool, but they do have a great onboarding process with a few mini games to help you explore the functionality of the mouse and sweep through some basic movements. If you're interested in getting the Spacemouse, I do have a link in the description down below. Alright, I think we have our finished assembly now up in CAD. Yeah, we'll give a test print of just the parts that we're missing, since we already have a few of the pieces fully built out already. Man, it's like deja vu up in here. Let's see if we did any better this time. Comment down below on what you guys think about this print job, and be honest, I can take it. And also drop a note on what you guys think I should print next. All right, I think we're finally all done with all these different iterations of this balancing jig. And as you can see, we were able to put the connecting rod on the jig and get it weighed. And compared to the factory numbers that we have, they were off by about a gram and 2/10, so 1.2 grams. Now that could just be scale calibration, so I'm not too worried about that. It's more if the measurements that we're getting from the jig are repeatable. And so far, I've taken it on and off a few times, and it seems to be holding just fine. There's good play in all the bearings, so I'm pretty happy with the result. We saved quite a lot of money, but I'm not gonna lie, it did take quite a few iterations to get here, but a lot of that was just me learning how to model properly. And I shouldn't even say properly, I don't know if this is the proper way to do it, but it seemed like it worked and it was functional. So the last thing, we're not actually going to leave it like this. I want to make this into a kit that other people can use. What we're gonna do is actually create a carrying case for it, or a storage case for it, so it's not just a bunch of loose parts. And there was a reason why I decided not to print, something like this arm here as an entire fixture by itself and have it in separate pieces, is that we can flat pack it into a carrying case. All right, I'm gonna tell you guys the truth. I just did all that and I totally forgot how big my print bed was. The design is too big, so I'm gonna have to pretty much do it all over again, but it's okay. Good practice, right?
Is this connecting rod down, sir? Oh, you even made a box. Damn, look at that. Where'd you get the bearings from?
They're skateboard bearings just from Amazon.
Oh, that's cool. So, if the motor blows up, then
it's on me.
you know it's this. Okay. I thought you were giving me chocolate. And I was like, damn, thanks.
As you can see, what was a $500 tool, we were able to replicate with very basic CAD skills and a 3D printer that you just set up and press print. The entire tool without the box costs about $2.53 in filament and about $10 in bearings that you can pick up off of Amazon. So $12.53 versus $500. Pretty easy decision in my mind. And just doing this one tool in itself basically offsets a third of the cost of the printer. Now, I must admit, just doing the connecting rod balancing jig is a little bit boring for the toy that we have, so I actually went ahead and designed a teardrop shaped shift knob. And here it is. So here is our teardrop shift knob. 2-inch top sphere tapering down to a 20mm base with the thread of 12 by 1.25, which is what you see in Subarus and 86s. And I also did a quick collar for the reverse lockout as well, also threaded. So you just kind of put this at the base and put this on top. Luckily, there is another 86 in the shop on the ground that's doing a turbo install that we can go and test fit in there. I think this looks pretty dang good, even with the reverse lockout functional there and taking up all that white space that used to be. I have to say I'm pretty happy with how it fits on the first try. You definitely feel the lack of weight, but because I decided to go with a longer shift knob, the extra leverage actually helps it to engage pretty quickly and smoothly. As part of this video, I'm going to print one more thing, and from a materials match perspective, this is probably going to be the most practical yet functional piece of 3D printing, and that's going to be an air intake NACA duct for the rear triangular piece of glass. Alright, so here's our first piece of external body / aero / cooling. The way that we printed this piece was using quite a bit of supports because of how much overhang there was with this inlet.
Look at that, NACA Duct.
It's like a $50 piece right there for like $3.
Trust me, Mikey bought this from like Rentless for like, the Rentless? Anyways, for 9/11 it was like $100.
I think for something like this, you just sand it and then clear coat. It's basically perfect. It's just plastic.
It's just plastic, man. Gotcha?
Yeah, I'm gonna try. All right, let's go deliver this NACA duct over to M-Tech Auto.
Oh man, oh.
Special delivery.
Oh, what is this?
What are you talking about? I thought you asked me for this.
An NACA duct?
Yeah,
What's that for?
for this car.
For what?
Air intake. For the cabin? There it is, the Audi TT that we raced all of last season with and came up in second place. I know second place, but we're gonna run it again this year. Hopefully the results are gonna be one place better. And yeah, we're gonna start putting on some of our DIY 3D printed aerodynamic and exterior parts. We will find a place for this duct, I think maybe for some cabin ventilation, to blow some air onto the driver's face to cool off and things like that. But there's actually a lot of work on the front hood in terms of venting heat.
So yeah, the current vent, it works, but I think it's not efficient enough. And also, to be honest, I don't think it looks like pretty good. It kind of a little bit ugly.
It's functional. Home Depot Aero. That's where everybody starts. But you know, I mean, it's effective, right? You have these girding flaps to make sure that the air going across it isn't like a blade, right? So it creates a little bit more low pressure here, right?
Yeah.
At least clean this up in terms of like ramping it up, so it's not a straight edge. So we can create a nice ramp.
And also for the fender vents, last time, first day at Passport, when it rained, somebody took a picture.
Was it effective? Was it like actually venting? These ones here, right?
These does the job.
Yeah.
But the fender one, only a tiny little bit of water drops comes out.
Okay.
But the rear one,
Yeah.
tons of water.
Tons of water was flowing
And
out.
also you can see the water mist is coming out
Yeah.
of the well.
I don't know.
What are you dummies doing?
We're talking about how we're kicking you off the team.
What is this? Whole wire authorized? What is this? Fuel tank? What is this?
Like
The plans?
what water is.
Oh my gosh. Yo, you guys are actually starting to get organized, eh? what contraceptive device are you holding right now? Yeah.
To funnel the.
I knew you needed this. I was gonna get you this for Christmas, dude. Oh, the quality
When
is
you're
actually
driving the car.
the quality is actually really high.
No, pull it close to your tummy. Right to.
Look at that! Look at the outline.
So while we're dropping off some stuff on this trip, we're actually gonna also be picking up some things for our future build. All right, what do you got for me right there? All right, so this guy right here, I'm gonna blur it out for right now because we're gonna make a future video on this. It's gonna go into the K24 FRS build. It's really fancy, and I'm really excited to show you guys when we can actually start putting this in the car. So the other thing that I'm picking up, I can show you. So this right here is a custom MTR forged center lock racing wheel. And I will admit to you that I don't actually have any cars that take a center lock because I'm not that baller. But we're gonna take this because it was actually a mismanufactured wheel from the factory with the wrong offsets. And because of center lock, you can't really run spacers or anything like that. We're gonna repurpose this wheel and turn it into a piece of functional furniture for the studio space. After all of that printing, what have we learned? Here are a couple of takeaways. Two of the things that we printed today are actually really good case studies. So we have our NACA duct and our shift knob. So let's first start with the NACA duct. This is something that I would say is a really good fit for 3D printing right now. One of the things is just thinking about the properties of the material. Now, NACA ducts traditionally are made out of plastic, so we're not really deviating too far away from the norm. So in terms of structural rigidity and integrity and temperature resistance, this all fits inside the wheelhouse of 3D printing, and the shape is actually fairly easy to print as well, with some support, but nothing crazy in terms of overhangs that would be difficult to achieve with a good 3D printer. But when we move on over to the shift knob, it's a bit of a different story. There's a reason why you don't see a lot of shift knobs being made from plastic, and part of that is you do want to have a little bit of weight inside a shift knob to help you with the smoothness of a throw. And if we take a look on the scale, this entire 2-inch shift knob weighs a whopping 30.8 grams. That's practically nothing. Even shift knobs that we do see today made out more of a plastic material typically have a metal core made out of steel to give that weight, and maybe they wrap Delrin around it to have a different texture, a different touch. So while it may be practical to print these from a manufacturing perspective, you probably will want to have some sort of metal core for longer lasting threading, as well as to give it some weight, which at the end of the day may not be worth the trouble. The other thing that we learned from printing the shift knob is that we really have to think about how a product is being used and where the forces are going to be introduced from, particularly the angle of the force. It was very easy for us to print vertically with the Z-axis moving up the shaft of the shift knob. However, thinking about it later, it would have actually been better to print the knob in this orientation with the Z-axis moving vertically this way. The reason for that is when we print it in this orientation, the Z-axis layers this way, but we introduce force on the shift knob in the X and Y axis. And when it comes to 3D printing, the Z layer axis usually is the weakest. So rather than have layers stacked on top of each other this way, we can do it this way. So when we try to bend the shift knob, the stress is on strands of fully extruded filament as opposed to layers that have been put together through heat. So while I probably wouldn't put this knob on a customer's car, I'd gladly run it for my own uses, especially if it's just for the sim rig. Now, if you guys are interested in supporting the channel, I will add some links in the description to the 2TrackMine website where you can pick up for just a couple of dollars the print files for the products such as the NACA duct or the connecting rod balancing jig. And if you don't have a 3D printer, I'm very happy to print them out for you and send them off. So where does this leave us? We've got this jig, but we haven't made any material progress on the FRS K24 Turbo DCT swap just yet. But don't worry, that's all gonna happen on a future episode when we start shaving grams off of these connecting rods. While building the jig itself is fairly trivial, to me, it's all about unlocking new capabilities. Instead of going online to shop for parts to fit my needs, I can now design and print things in-house. And while there have been a few hiccups here and there, I honestly do think that now is the perfect time to add a 3D printer to your home garage and expand your toolkit as a DIY enthusiast. Using a premium printer these days really does feel like you can just flip on the on switch and print. Based off of my research, I've added a few options for you to consider in terms of printers and filament that you can find in the description down below. If you've enjoyed this content, then consider dropping a like, a comment, or even subscribing if you want to see more. And with that, we'll catch you on the next one. What's a NACA duct for anyway?